In Math 1201 video 12, we're going to take a look at properties of the determinant. Let's jump right into the properties. Theorem 1 says if we have an n by n matrix and C is any scalar number, so in our case C is usually going to be a real number, although C could be a complex number as well, then we have the following. First, determinant of A transpose is equal to the determinant of A. Second, the determinant of C times A is equal to C to the power of n times the determinant of A. So the n here is the size of our original matrix A. This is very important. I'm actually going to walk from the camera to circle this here and this up here. Make sure you highlight those. Most students tend to forget that n that comes along in property 2. Third property is that determinant of A times B is equal to determinant of A times determinant of B. And finally, we have two more. Property 4 is determinant of A inverse is equal to 1 over the determinant of A. And the last one, property 5, is that the determinant of A to the power of K is equal to the determinant of A all to the power of K. We are going to prove a couple of these properties, and I'm going to leave a couple of them for you to think about as well. The first property we're going to prove is property 2. Property 2 says determinant of C times A is equal to C to the n times determinant A. So let's start off with a general matrix A, and we're going to scalar multiply all of our entries by this scalar number C. So what we're going to do is we're going to take this matrix CA and we're going to perform n elementary row operations. So we start here, we divide row 1 by C. And then we divide row 2 by C. And we keep going until we take row n and divide row n by C. So we have in total n elementary row operations that we're going to do on this starting matrix. After we do these operations, we end up right back to where we started. This is matrix A. So here's the equation we get. We start with matrix CA. We do n elementary row operations on this matrix, and that lands us back to the original matrix A. If we take the determinant of both sides, we get this expression. Each of these elementary matrices in here represent the operation 1 by C times one of the rows. So all of these elementary matrices are type 1 elementary matrices. Their determinants are all going to be 1 over C. So let's fill that in. We know that determinant of A will be equal to, we're going to get 1 over C times 1 over C times 1 over C n times. So we get 1 over C to the n times the determinant of CA. And when we solve for determinant of CA, we get exactly that expression that we're looking for. Property number 3 is a bit of a pain in the butt to prove because we have to divide it up into two cases. The first case is we're going to look at the case where either A or B is not invertible. Now, without loss of generality, let's take A to be the matrix that's not invertible. We know that this means determinant of A is equal to 0. Now, another little nice fact about matrices is that if A is not invertible, when we try to form a product with A, it's also not going to be invertible. So the matrix A times B will not be invertible either. So we also get for free that the determinant of A times B is equal to 0. So knowing that information from before, we can put together that equation that we need. We know that the determinant of A times B is equal to 0. 0, of course, is equal to 0 times any number that this determinant of B could be. And we know 0 is equal to determinant of A. So we get that determinant of A times B is equal to determinant of A times determinant of B. Case number 2 is the trickier case because we have to resort to elementary matrices. So let's assume that both A and B are invertible. If A is invertible, we can express A as a product of elementary matrices. So this is an equation that we saw in the matrix chapter. And what we're going to do is we're going to multiply both sides of this equation by the matrix B. After we've done this, we're going to apply the determinant to both sides. So here we're going to get determinant of AB. And on the right-hand side, we know we can break apart each of these elementary matrices, and that's going to give us this expression. We've got determinant of EK inverse all the way up to determinant E1 inverse multiplied by determinant of B. Now the really nice thing about having determinants of elementary matrices is that we're going to be able to combine all of these back together into one determinant. So we're going to be able to rewrite this right-hand side as determinant of EK inverse all the way to E1 inverse times determinant of B. And all of that is still equal to determinant of A times B. Next, take a look at this expression inside the determinant. What is this expression equal to? Well, this is just A from what we had before. This is where we started. So what do we get? If we replace A in here, we get that the determinant of AB is equal to determinant of A times determinant of B. In order for us to prove the fourth property, which is the last one we're going to do, we need to use the previous property. We're going to start with one of the matrix inverse equations. So if A is invertible, then this equation is going to hold true, and we can take determinant of both sides. Now let's try to simplify the right-hand side. What is the determinant of an n by n identity matrix? That's just equal to 1. This is a diagonal matrix with 1s on the main diagonal. So we multiply all of those 1s together, we end up with the value of 1 for the determinant. Now, here's where we use property number 3. I'm going to split this apart into two separate determinants. So I'm going to write this as determinant of A times determinant of A inverse. Now determinant of A is a number, and in fact we even know that determinant of A is not equal to 0 because A is invertible for property number 4. So this lets us simplify a little bit. We can put this determinant over here underneath the 1. So essentially I've divided both sides by determinant of A, and this is what we get fully simplified. So I know this is a little weird for me to do in video form, but this is what I want you to do as homework. I want you to think about property 1. Property 1 says that the determinant of A transpose is equal to the determinant of A. Think about why that's true. Why would those two matrices have the same determinant? And I want you to try to tie that into the theorem about cofactor expansion. Second, I'd like you to prove property number 5. In order to prove property 5, you're going to have to apply property number 3. And you're going to have to apply property number 3 k times. Where you're going to find these properties most useful is when you're given questions where you know what the determinants of your matrices are, but you don't necessarily know exactly what your original matrix looks like. Here is such an example. So we have A and B as 2 by 2 matrices. We know that the determinant of A is 3 and that the determinant of B is -5. What we want to do is use that information to calculate the following 4 expressions. Let's start with determinant of A inverse. We know by property number 4 that determinant of A inverse is equal to 1 over the determinant of A. Now this is something we know how to solve for. What is the determinant of A? The determinant of A is equal to 3. So we have determinant of A inverse is 1/3. Next, let's look at determinant of A times B. By property number 3, we can break this apart into determinant of A times determinant of B. And we know what each of these numbers are. So we fill in determinant of A is 3, determinant of B is -5. So this determinant should be -15. Here's an example of property number 5, determinant of B cubed. Well, this is equal to determinant of B, and we move that 3 outside. So what we're going to do is we're going to fill in determinant of B as -5, and then we're going to cube that. So what is 5 cubed? That's 125. So our final answer, because of this negative sign, is going to be -125. You, yes, you, right there. Pay attention, because this is the place that everybody's going to mess up, right here on this kind of question. What is this? This is the same thing as saying determinant of A times -1. So this is like C times A. How do we bring this -1 outside? Well, we have to raise this -1 to some power. What's the power that goes here? Well, it's going to be the size of matrix A. Remember that A was 2 by 2. So these numbers here tell us which power to put as the exponent of this number that's on the inside. So when we simplify this, -1 squared is just 1. So we're going to get that determinant of -A is really just equal to determinant of A. And determinant of A is 3. Here's another one of those random cases where many students make mistakes. It is not true in general that we can break up a determinant using addition. By that I mean if there's an addition of matrices inside the determinant, we can't break that apart into determinant of the first matrix plus determinant of the second matrix. It just doesn't work. So what I've done here is I've thrown up an example just to illustrate that equality really never holds for matrices. So here we have A, B, and I've also taken A and B and added them together to create this 2 by 2 matrix. So let's calculate determinant of A. What is the determinant of this 2 by 2 matrix? Well, it's upper triangular. So all we have to do is multiply the numbers here to get that determinant of A is equal to -3. Next, let's calculate determinant of B. B is lower triangular, so let's multiply these two entries to get determinant is equal to -2. Last but not least, let's find the determinant of A plus B. Here we will have to use the weave method if we're going to get -10 minus 8 more for -18. So you can see that this determinant is definitely not equal to the sum of these two numbers. Don't forget that!